Okay. One of the last little bits of probability now we have to look at are the Bernoulli Trials, which basically look at successes and failures, and you may have to manipulate what is a success and what is a failure in a particular question. A number of repeated trials are called Bernoulli trials if they are independent, they are identical, and each trial has only two possible outcomes, which may be termed success and failure. So it doesn't necessarily have to have only two possible outcomes, but you have to be able to manipulate the outcomes as a success and failure. Like, for example, it still could be the amount of times a 5 is thrown on the dice. Obviously, there's not just two outcomes for a 5 on a dice. You obviously can get 1, 2, 3, 4, 5, and 6, but for a Bernoulli trial, you're going to manipulate it. So 5 is your success and every other number would be your failure. So example, for repeatedly tossing a coin and being interested in the number of heads, that's a Bernoulli trial, because every single time you toss that coin, they are independent. One result doesn't affect the other result. Okay. We would call getting a head in a single trial a success, and then the tail is the failure. Other examples of Bernoulli trials are, was a newborn baby a girl? So obviously girl is the success, boy is the fail in that case. Did a voter vote for a particular candidate? So the candidate is, the particular candidate you're talking about is a success, and every other candidate then would be the failure. Did a shopper buy a particular product, and so on. You get the idea. Okay. So as we go into these, there are, so again, many trials appear to have more than two possible outcomes, but by an appropriate grouping of the possible outcomes, we may consider that there are only two. Okay, so again, there's examples here if you want to read through them. For example, suppose a dice is thrown repeatedly and we are interested in the number of times we get a 5 or a 6, then the 5 and the 6 is the success, and the failure is every other number. For a single Bernoulli trial, it is usual to let P be the success and Q be the failure. This comes in quite important in a little while, because we will end up talking about a formula and it'll take into account P's and Q's. Because we must get either a success or a failure, then P plus Q has to be equal to 1. Okay, because I've nothing else. I have a Bernoulli trial is based on the fact that you have a success or a failure, so one or the other. Okay, so therefore the failure is 1 minus the success. Okay. Right. When I talk about Bernoulli trials, I have to account for there being 3 types of question I can be asked here. Okay, so the first type, okay, would be finding the place of the first success. Okay, so for example, what is the probability of throwing a head for the first time on the third throw? So in this case, the first 2 must be tails and then the third one must be a head. What is the probability that the first success occurs on the 4th trial? So that would mean that there has to be 3 failures and the 4th one specifically has to be the success. Okay. Really important here that the formula is not necessarily needed. Okay. If it was really, really large numbers, like maybe if we were talking about 20, 30 trials, you definitely would need the formula. But in general, we're only talking about 5, 6, 7, 8 trials. So you don't necessarily need the formula. Okay. But it's there for you if you want to use it. Suppose a single Bernoulli trial has the probability P of success P and a probability of failure Q, then the probability of the first success occurring on the 9th trial is Q n minus 1. Okay, so basically up until n, I have to have failures all of the time, and then the next one, so multiplied by the success on the last time. Okay, the probability of the first failure occurring on the nth trial is P n minus 1 Q. You'll find that you actually don't tend to use this formula for this first type anyway. Okay, so let's take an example. For a single trial, the probability of success is 0.4. Okay, therefore the probability of failure, I'm just going to call it PF, has to be the opposite. It has to be 0.6. Okay, so that's the first question answered. If the trials are repeated, find the probability that the first success occurs on the 4th trial. Okay, well, that means if the first success occurs on the 4th trial, well then the 3 before it have to be failures. So, So I have to have 0.6 and 0.6 the second time, and 0.6 the third time, and the fourth one is now a the fourth one is a success. Okay, so in that case, so if I use the formula in this one, for instance, 0.6, n is equal to 4 because I've got 4 trials. Okay, so n equals 4. So n minus 1 is 3, okay, which is effectively the exact same as multiplying them by themselves 3 times p. Okay, either way, whichever option you use, the formula or not, I'd be a fan of not using the formula because you have to remember the formula, they're not in the log tables, is 0.0864, and usually to 3 significant figures is what we give these numbers, okay? 3 or 4 significant figures. If the trials are repeated, find the probability that the first failure occurs on the third trial. So in this case, again, I'm not going to use the formula here. I've no need to. Okay. If the first failure occurs on the third time, then the first 2 must be successes. So 0.4 times 0.4. And the third one has to be a failure. So 0.6. Okay. This first type is very straightforward, I think, anyway. Oh, sugar. Where did I go? Okay. A fair die is thrown repeatedly. A success is getting a 5 or a 6. Find the probability of getting the first success on the third throw, fifth throw, eighth throw. So the probability of success here, okay, so P is getting a 5 or a 6. Okay, now there's 2, so there's 1 5, 1 6, so 2 options out of a total 6. So that's a 1/3 chance of success. So the probability of failure is 2/3. Okay, and we tend to just use P is equal to 1/3 and Q is equal to 2/3. Okay, so find the probability of getting the first success. So 1/3 on the third throw. So that would mean that the first 2 are failures and the third one is a success. So 2/3 times 2/3 times 1/3, we'll get 4/27 there. Okay. The fifth throw, okay, I'm not going to actually do the 8th throw because we get the idea, but the 5th throw, actually I'll do the 8th one, I'll skip the 5th, so the 8th is a bit bigger. So I can go, in this case, 2/3 times 2/3 times 2/3 times 2/3, okay, and do that 8 times. However, this is an example of where the formula tends to be, and it's not even a formula because, like, when I start to do this, I need to, if I have the probability of getting a success on the 8th throw, well then I've got 7 2/3 multiplied by themselves. So 2/3 to the power of 7. So I have to have 7 failures, and the third one then has to be my success. Okay, so in this case, I would take 2/3 to the power of 7 times 1/3. Okay, and I'd end up getting the probability is 128 over 6,561. Okay. Right, type 1 is very straightforward, very easy. Type 2, not that it's any way more difficult, but it does require a little bit more thinking. Type 2 is the exact number of successes in a particular number of trials. Okay, so for example, if an event happens 6 times, what is the probability of getting exactly 2 successes? Okay, now these successes can happen in any of the 6 trials. Okay, so this time there are different, like, positions or whatever that it can be in. So we must take into account that there are 6 choices for this. Okay, and there are 2 places to be placed. Okay, so a formula is not strictly required here either. Okay, but it is certainly useful. Okay. So in this case, we have suppose a single Bernoulli trial has a probability of success P and a probability of failure Q, then the probability of exactly or successes in N trials is given by. So I first have to get my combination, okay, because there are 6 choose 2, there are 6 combinations that this could happen, okay. P, my probability of success, okay, times Q, my probability of failure, okay. So N, the total number of trials, and or the number of trials that I want a success in, okay. So again, you don't have to use the formula here, but it is useful. A fair die is thrown 5 times. Find the probability that a 4 appears exactly twice. Okay, now the probability that a 4 appears at all is 1/6. There is only one 4 on a dice. Okay, but find the probability that that comes up exactly twice. Okay, so I have 5 times and I want 2 of them. So I want 2 of those 5. I want to choose 2 of those 5 to be successes. So just be careful here. Note your difference between your combinations and your permutations. Okay. I'm not strictly thinking about an order. I am saying there are 5 and I want to choose 2 of them as my successes. Okay. So how many different ways are there to choose those 2 successes from 5? So just be careful that you are using combinations, not permutations. Okay, so that's 10. Okay, so I've got 10 times 4, I have to get twice. Okay, so I need 1/6 twice. Okay, now I'm going to go and I'm going to use the formula, but you don't have to use the formula. So my 1/6, I'm going to use it twice. Now I could just say 1/6 times 1/6 either. Okay, and my failures then have to happen all of the other times. Okay, so if my 1/6 happens twice, then my 5/6 has to happen all of the other times within that 5. Okay, so 5 minus 2 is 3. Okay, and then I've got 10 times 1/6 squared times 5/6 to the power of 3. Okay, and I'll get 625 over 3,888. Okay, so you're multiplying all of these numbers together. And again, if you want to go back and just see there your formula, you're taking your combination and you're multiplying it by your successes to the power of the amount of times you want that to happen, multiplied by your failures to the power of the amount of times you want that to happen. Okay, and again, like I said, you don't have to use the formula. You know that you get 1/6 twice, so 1/6 times 1/6. And if I'm getting 1/6 twice, then everything else, so the rest of the 5 times, has to be the 3/6. Or sorry, the 5/6. Apologies. Okay. Slightly different question here in that it's the way it's worded. It says a die is thrown 8 times. What is the probability that we get at most 2 6s? Okay, so at most 2 6s means that I can have no 6s, I can get 1/6, or I can have 2 6s. And I need any one of them to occur. So the probability that I get at most 6s, I have 3 choices. I have no 6s, 1/6, or 2 6. Okay, so first of all, the die is thrown. I have 3 different probabilities here to calculate. I have the probability that I get no 6s, the probability that I get 1, and the probability that I get 2. Okay. So let's say the probability of 0. So 0 6s or no 6s. Okay. is I have 8 and I'm going to choose 0 of those. So the chances that I have 8 trials and none of them come up as a 6. Okay, means 1 6. Okay, so it's a dice. So a 6 has a 1/6 chance on a dice. Okay, but that's going to come up no times, and that means all the other numbers come up every time. So that's coming up all 8 times. And that is 0.23257. The probability of getting 1 6. Write in words. Okay. I have 8 and I choose one of those times to get a 6, which means I get only 1/6, or 1 success rather, and that means I have 7 failures. Okay, so I don't get a 6 7 times. So 0.37211. And finally, the probability of 2 6s. I have 8. I want to choose 2 places in which I get 2 6s. So that means the 6 now comes up twice. The failure, the rest of the numbers, which is 5/6, comes up 7 times. Okay, just throw that into the calculator. 0.26048. Okay, and here we have, remember, I want any one of these events to occur for it to satisfy my probability. So add those all together, 0.86516. So there's a fairly high chance that if you throw a dice 8 times, that a 6 is going to come up. So that probability there makes sense. And it is always useful as well, just to think about your probability making sense as well. I don't know why that keeps happening. Okay, my pen also, I don't know why it won't change from red, so just bear with me on that one. Okay. Okay. I'm just going to see, can I change the colour of my pen? Okay, hopefully this will change now. Okay, right, a fair die is thrown 5 times. Find the probability that a 4 appears exactly once. Okay, we're going to have to stick with red pen, I'm afraid, so hopefully you all can read red pen. A fair die is thrown 5 times. Find the probability that a 4 appears exactly once. Okay, so we are talking about 5 times. So 5, choose 1. A 4 appears exactly once. So we're talking about a dice. So 1/6, 1 time, and the rest of the numbers then are going to occur 4 times. Okay, so we've got 5, choose 1, which is going to be 5, times 1/6 times 5/6 to the power of 4. Okay, and you do tend to get quite large probabilities here, or long kind of decimal probabilities, and it's usually to 3 or 4 decimal places. Okay, find the probability that a 4 does not appear at all. Okay, so if it doesn't appear at all, it's coming up 0 times. Okay, so I've got 5, choose 0. And that means I've got 1/6 doesn't come up at all. 5/6 comes up 5 times. Okay, so 5, choose 0 will just be 1. 1/6 comes up 0 times. And 5/6 comes up all 5 times. Okay. And we should get, I'll just put this into my calculator now. 5 choose 0 times 1/6 to the power of 0 times 5/6 to the power of 5. So the 5/6 comes up every time. Okay. And the probability that 4 does not appear at all in 5 times is 0.409. We'll leave it there. Okay. Find the probability that a 4 appears at least 4 times. That word at least, you've got to be really, really careful of. Okay. That word at least means that I have to calculate 3 different probabilities here, because 4 different probabilities. I have to have the probability that it comes up none times, the probability that it comes up 1 time, the probability that it comes up 2 times, the probability that it comes up 3 times, and the probability that it comes up 4 times. Okay. So we have the probability that it appears exactly once. We have the probability that it doesn't appear at all. So we have both of these. So you have to calculate the probability that it comes up exactly 2 times and the probability that it comes up exactly 4 times. Okay, so that's the first question that I want you to finish off. So you can pause the video here and have a go at it if you want. Okay, third type of trial is you have the kth success in the nth trial. Okay, so what is the probability of the 5th success happening in the 8th trial? So a fair dice is thrown repeatedly. What is the probability that the 3rd 6 occurs on the 8th throw? So this case, again, you just have to think about these probabilities a bit. In this case, there must be 7 trials in which exactly 2 6s were thrown. Okay, and on the 8th one, there must be a 6. So I'm actually going back to my type 2 here. Okay, where I have 2 successes in 7. So I can still use this formula here. Okay, so I've got 2 successes in 7, and remember, and in probability is always an 8, and the 8th one must be a 6. Okay, so I have here a fair die is thrown repeatedly. What is the probability that the 3rd 6 occurs on the 8th throw? Okay, well, if the 3rd 6 occurs on the 8th throw, then I must have 2 6s in 7 throws. Okay, and the next one must also be a 6. Okay, so in this case, I'm going to just use my logic from the first one, that I have had 7, so there are 7, and within that 7, I'm choosing any 2 successes, because it can be any one of those successes. Okay, and actually the better way to write this, and the way you'll see it written, is 7 2. Okay, so 7 choose 2. In that 7 choose 2, I have, and again, I'm talking about 1/6 because it's a dice, and I'm just talking about the number 6. So a 6 has a 1/6 chance of coming out in a dice. It has to occur twice. It has to not occur, so all the other numbers, 5 out of 6, has to occur the rest of the time, so 5 times. Okay, and that will get you, we've got 7 choose 2 times 1/6 squared times 5/6 to the power of 5. Okay, So that will get you 0.2344. It's a big long decimal. We'll leave it at 2344. And multiply that a 6 now occurs on the next one. So on the 8th row. So I'm going to multiply it by another 6. Multiply it by the 6. So take my answer, multiply it by 1/6, because the very next row now, I've done 7, this is the 8th. My very next row now has to be a 6, 0.039. Okay, so you'll see your probability does actually drop quite a bit there. Okay, and so it should. And your final answer is 0.039. Okay, last question. A coin is biased so that a tail is 3 times as likely to occur as a head. This coin is tossed repeatedly. What is the probability that the 7th head occurs on the 10th toss? Okay, I want you to pause the video here for a second, and I want you to have a think about this question. Okay, so this first bit is really important. A coin is biased so that the tail is 3 times as likely to occur as a head than a head, sorry. Okay, so have a think of that one. Okay, so we have, for any trial, okay, in this case, let the probability of a head be X. Okay, because I don't know. A coin is biased so the tail is 3 times as likely to occur as a head. So let's say the head is equal to X, or the probability of the head is equal to X. Okay, so then the probability of a tail is 3X. Okay, so this bit here is really important because these are kind of the real tricky questions that will catch people out. Okay, so then the probability of a tail is 3X. The coin is tossed repeatedly. What is the probability that the 7th head appears on the 10th toss? Okay, so specifically now, the 7th head has to appear on the 10th toss. So that means that there are 6 heads in 9 throws. Okay, now I can actually figure out this probability here. Okay, because I have X plus 3X, and we know that it has to add up to 1. So 4X is equal to 1, X is equal to a quarter. Okay, so the probability of a head is equal to 1/4. Probability of a tail is equal to 3/4. And I am well aware you can do that in your head as well. The coin is biased so the tail is 3 times as likely to occur as a head. So if it's 3 times as likely, you have to be dividing by 4. So 1/4 and 3/4. Okay, that's an algebraic way of doing it if you are thinking more algebraically. Okay, so 6 heads in 9 throws. Okay, that means that you've got 9, you're choosing 6. Okay, your 1/4 for your head has to have occurred 6 times. There has to be 6 successes. And that means that if there's 6 successes, there's only 3 failures. Okay, I'm actually going to do this all in one, because I know at the end that now my 7th one, okay, or my 10th one rather, I've got my 9 here, so that's my 6 heads in 9 throws, and the 10th one, okay, has to be a head. The next one, the very next one, has to be a head. So multiplying it by a quarter. And that leaves me with, okay, quite a large fraction, 567 over 262 And you're left with a tiny little probability. And again, remember, that makes sense. Okay, because the chances of you getting the 7th head on the 10th toss, and remember, the head is less likely. Okay, so for you to get 7 of the less likelies in 10, okay, must carry a very low probability. Okay, that's your final answer. Okay, these questions are hugely important. They always come up. Okay, it's either this or conditional probability a lot of the time that comes up on the exam question. So make sure that you've gone through each of these sections and that you do understand them fully.